The combination of the interconnect delay and the LUT delay forms a single logic level. In this example, we have 3 levels of logic. The critical path delay is about 8.9 nanoseconds in this example, of which 7.4 nanoseconds is made up of interconnect delay. This may or may not be typical for you, since internal delays will of course vary by family and speed grade. But in our case, we're just going to work with this for an example. Always keep in mind that your synthesis tool will decide how your logic equations will map to the LUT architecture. So it will decide how many LUTs and how they are connected together. So depending on your coding style, the synthesis tool might choose to code some logic in series, as in this example, but depending on the type of component you're building, your synthesis tool might be able to build that logic in parallel. Fortunately, synthesis tools are getting better at mapping logic to parallel LUTs. The delay associated with the LUT is also very small, less than 0.5 nanoseconds typically. However, at the design level, it can appear that performance is highly variable, and you should appreciate what causes this to happen. The number of LUTs you have in series may be high, and thus the total delay on a critical path may be too long. The routing delays with the newest devices are nearly equivalent to LUT delays, not quite as in the case of this example. In fact, many of us use this way of estimating timing. We call that the 50-50 rule, where half your delay is routing and half your delay is logic. Each time the logic maps into multiple logic levels, you simply add more connection delay. So the delay increases in steps each time you exceed 4 inputs. If you could somehow always build logic with 1 LUT delay, you would be operating at peak performance or very high speed. You also should know that the implementation tools can try to place logic closer together in an effort to shorten your net delays. So here are a few things you should remember about coding styles for lookup tables. First of all, try to maximize the number of inputs to each LUT so that you can obtain the most logic out of the FPGA. Also, instantiate the appropriate LUT primitive if necessary, and if you want to learn more about LUT primitives, you can refer to the Xilinx Unified Libraries Guide. This is provided for you when you install the ISE software under the Help menu, and then you go to Software Manuals. Or if you want, you can go to support.xilinx.com and you can go look for the Xilinx Unified Libraries Guide there. A logic level is 1 LUT plus 1 net delay. So whenever we talk about multiple logic levels, we're talking about multiple nets and multiple LUTs cascaded in series. Synthesis tools and your coding style will often determine how many logic levels there are in every path of your design. But this, of course, will vary. But we're going to look and try to highlight in this presentation a number of cases where the coding style is pertinent. As this slide shows you, originally, when you built a 4-to-1 MUX in an older device family, the MUX was built entirely of just the lookup tables. In this case, a 4-to-1 MUX would use 3 LUTs and be built with 2 logic levels. Pretty good performance, but as you make the MUX larger, the delays will increase quickly, and you'll end up with multiple logic levels and hence slow performance. With the newer device families, you have access to the F5, F6, F7 and F8 MUXs. These are used to build 4-to-1, 8-to-1, 16, and 32-to-1 MUXs, respectively. In this example, we use the MUXF5 to group the outputs of the 2 LUTs in the same slice to make a 4-to-1 MUX. This gets better speed than the older implementation because a LUT delay and the routing delay between the MUXs is saved. In this case, it uses 2 LUTs and uses 1 logic level, better than our original result on both counts. So by using these MUXs, you save LUTs and get better speed. Wow, win-win scenario. Remember that this requires the 2 LUTs associated with the F5 MUX. You can't just group any lookup tables in this fashion. Likewise, there is dedicated routing associated between the other MUXs to create the faster and larger multiplexers. So you can't just separate these resources out. You have to use the ones associated with a single CLB. Finally, be sure to use your schematic viewer to make sure that your synthesis tool infers these resources correctly. Although the primary use of a MUXF5 is in creating larger multiplexers. It can also be used in the generation of any logic function of up to 5 inputs. The connectivity between the LUT and the MUXF5 means the two 16-bit truth tables associated with each LUT are concatenated to form a single 32-bit truth table. Note that while MUX behavior can be inferred in most cases, it will require the use of a case statement in your HDL. The MUXF5 can implement some functions of up to 9 inputs, providing the inputs can be separated into 2 functions of 4 inputs. Unfortunately, not quite as useful as you might think. However, this will require you to instantiate the appropriate MUX primitives to construct your system in this way. This slide shows how the F6, F7, and F8 MUXes can be combined to create 8-to-1, 16-to-1, and 32-to-1 MUXes respectively. Because the F5, F6, F7, and F8 MUXes can be inferred automatically by all the high-end synthesis tools, most designers do not instantiate these resources. However, a case statement will be required. You should also note the specific sizes of the MUXes that can be made with each of the dedicated MUXes. The F5 requires 2 LUTs in 1 slice. The F6 requires 4 LUTs in 2 different slices. The F7 requires 8 LUTs in 4 slices, or 1 CLB. And the F8 requires 16 LUTs in 8 slices for 2 CLBs. And of course, as I mentioned before, all of these LUT combinations are fixed. You can't just pick and choose which LUT's going to be combined. In this exercise, see if you can build the MUXes that we're describing here. These are not quite as easy as you might think, but take a few minutes and draw it out. In fact, I encourage you to refer to the last couple of slides about these resources. Calculate how and which type of MUXes will be necessary to create these. So we have, first of all, on the left-hand side, we have a large multiplexer with 8 inputs and 3 select lines with a 12-bit output. Our second multiplexer, we've got 5 inputs with 3 select lines and a 12-bit output. So grab some paper, pencil, and have some fun with this. Spend a few minutes and then come back and you can look at the answer. Well, the first question, which is the 8-input, 3 select line, 12-bit output multiplexer, can be thought of as being an 8-to-1 MUX replicated 12 times, since it has a 12-bit output. Now recall that the 8-to-1 MUX uses 4 LUTs plus an F5 and an F6, which equals 2 slices. So the entire MUX will be that configuration, okay, times 12 for 12-bit output. It also is extremely fast, since each of the LUTs are in parallel and the delay of the F5 and F6 MUXes is almost negligible. The delay is just 1 level of logic, and that's pretty amazing when you consider that previously this would be just built with LUTs in series. Multiple levels of logic and get horrible performance. But now that you get the dedicated MUXes, it just flies.